archival black and white footage of Gallipoli 1915 and Dieppe raid 1942. Troops pinned on beaches, vehicles sinking in surf. Cut to dramatic slow-motion waves crashing against a modern ship hull. Overlay equation. GM equals KM, KG metacentric height formula. Tense, low music. Asterisk. December 1941. British commandos hit the beaches at Viagso, Norway. The plan was simple. Get men and heavy weapons ashore fast. Reality? Landing craft broached in the surf. Vehicles drowned and the assault bogged down for hours. Fast forward 80 years, and the physics hasn't changed. To turn an open ocean warship into a floating pier for 1,000 troops and their armored vehicles, you have to flood a cavernous internal dock while the ship is underway. On paper, naval architecture says this should destroy the vessel's stability. Yet the USS Comstock, LSD-45, does exactly that routinely. Today, we're dissecting the civil infrastructure miracle that makes rapid response at sea possible and why it's still a brutal engineering compromise. Map of current Pacific/Indian Ocean flashpoints, Strait of Hormuz, South China Sea. Animated overlay of Amphibious Ready Group ARG, with USS Comstock highlighted. Cut to 11th MU Marines loading vehicles at San Diego. Stock footage of Comstock at sea, while deck open. Asterisk. Modern conflict doesn't wait for friendly ports. Adversaries with anti-access/area denial, A2/AD. Missiles can turn traditional harbors into kill zones. The U.S. Navy's answer is a Marine Expeditionary Unit. Roughly 2,200 Marines spread across 3 ships. USS Comstock, a Whidbey Island-class dock landing ship, is a logistics backbone. Officially, it embarks 402 Marines plus a 102 troop surge, about 500 total. Viral titles say 1,000 troops, but the real number is the full combined force the ship enables when paired with its ARG sisters. The economic and military driver is brutal. Project decisive combat power onto any coastline in under an hour. No infrastructure required. 3D CGI cutaway of USS Comstock hull. Highlight well deck, 440 feet long times 50 feet wide. Animated cross-section showing empty well deck flooding sequence. Real-time physics simulation of free surface effect. Ship healing dramatically as water sloshes. Graph. Metacentric height GM dropping below 0 equals capsize risk. Side-by-side comparison. Solid ballast versus free surface liquid. Asterisk. Here's the first principles problem. Any floating object obeys Archimedes. It displaces its own weight in water. But stability depends on metacentric height, GM. The distance between the center of gravity, G, and the metacenter, M. When you flood the well deck, you create an enormous free surface. For 140 feet by 50 feet of seawater that can slosh side to side. That liquid's moment of inertia skyrockets, the virtual rise of G. In extreme cases, GM goes negative and the ship rolls over. Add 70-ton M1 Abrams tanks, Humvees, artillery, and fuel trucks rolling on and off. Their shifting center of gravity compound the issue. The well deck is essentially a 22,000 square foot swimming pool inside a 16,000-ton ship. Traditional naval architecture says you don't do this at sea. You do it in dry dock. Yet Comstock must do it while holding station in 4-foot waves. Exploded 3D view of ballast tanks, pumps, and stern gate. Animated ballast control system. Water pumping in slash out in precise sequence. Time-lapse of actual well deck flooding from Navy footage, slowed for clarity. Cut to LCAC hovercraft exiting at 40-plus knots over the beach. Load distribution diagram showing deck reinforcements. Cross-section of high-strength steel plating. Asterisk. So, how did engineers solve it? Not with magic. Pure systems engineering. The well deck is a precisely engineered box with a massive hydraulically operated stern gate. Before flooding, the ship's ballast control system, dozens of tanks along the sides and bottom, pumps thousands of tons of seawater in a choreographed sequence. This keeps the ship trimmed level and maintains positive GM even as the well deck fills. Pumps can move water at rates measured in hundreds of tons per minute. The hull itself uses high-tensile steel with longitudinal framing to handle point loads from track vehicles. Decks are reinforced where tanks park. The entire system is computer-controlled today, but the 1980s design was already sophisticated enough that Comstock can flood, launch 4 LCACs, each carrying 60 to 75 tons at 40 knots, and recover them without ever tying up at a pier. LCACs themselves ride on an air cushion, reducing ground pressure to that of human foot, so they can cross the surf zone and climb beaches that would swallow conventional landing craft. The ship becomes a mobile logistics hub, well deck for heavy stuff, flight deck for CH-53 and MV-22 vertical assault. It's civil infrastructure at sea. Think a temporary port that sails 20 knots and disappears when the mission ends. The trade-offs. Real engineering is compromise ***. Graph comparing Comstock speed, 22 knots, versus newer LPDs. Fuel consumption numbers. Vulnerability heat map. Well deck open equals radar signature spike. Maintenance backlog stats, if public. Side by side. Cost of one LSD versus commercial RORO ship. Asterisk. Let's be skeptical. This isn't flawless. Flooding takes 15 to 30 minutes. Fast in military terms, but not instant. While the well deck is open, the ship is more vulnerable to sea state and enemy fire. The 4 Colt peel stick diesels deliver 33,000 shaft horsepower, but they're thirsty. Range is 8,000 nautical miles at 20 knots, yet sustained high-speed ops burn fuel fast. Maintenance is constant. Salt water in the well deck corrodes everything. The class is now 35-plus years old, and while load-bearing is impressive, the ship can't carry the heaviest modern vehicles without careful planning. Compared to commercial roll-on/roll-off ships, Comstock is vastly more expensive per ton of cargo moved. But those commercial ships can't survive in a contested littoral, can't launch hovercraft at sea, and can't maintain stability while flooding a 440-foot dock. The verdict in economic reality ***, future amphibious concepts, if any public renders, versus Comstock. Cost breakdown infographic, acquisition, $300M in 1980s dollars. Operating costs. Final shot. Comstock at Seawell Cax departing at sunrise. Uplifting but realistic music. Asterisk. Is this technology viable for the future? Absolutely, for the next decade or two. The Whidbey Island class has proven the concept, so well that newer ships still copy the floodable well deck. But rising maintenance costs and evolving threats, hypersonic missiles, drone swarms, mean the Navy is already looking at distributed, smaller, cheaper platforms. Economically, one Comstock costs roughly the same to operate annually as a small commercial fleet, yet its ability to deliver a reinforced Marine battalion anywhere on Earth without permission remains priceless. In the end, human ingenuity didn't break the laws of physics. It worked around them with pumps, steel, and relentless attention to metacentric height. The ocean still sets the rules. We just learned how to negotiate. Channel logo, subscribe graphic, suggested videos on naval architecture, or LCAC tech, and screen with sources. Asterisk. If you want to dive deeper into free surface effect or why hovercraft changed amphibious warfare forever, drop a comment, like, subscribe, and I'll see you in the next episode, where we tear apart another piece of infrastructure that shouldn't work, but does.